Better College, London. The title of his talk is on some sharp spectral inequalities for Schrödinger operators on graphs. Please.
Thank you. Very grateful for inviting me here. When there was this program, I gave a talk, and it was nothing to do with graphs. So I thought my participation in the program was very useful because now I have a talk on graphs. I'm going to talk about basically elliptic inequalities on graphs. So just let me remind you what it's all about. So we begin with the Schrödinger operator in a multi-dimensional case. The microphone works, right? I hope. Yeah. Okay. So and then typically, if potential goes to 0 at infinity, then spectrum is continuous on a semi-axis, and then might have some negative eigenvalues. And elliptic inequalities say that if you take the sum of the absolute values of the eigenvalues to the power gamma, then you can estimate it through basically a numerical range of phase volume. And if you integrate with respect to psi, then you get this inequality, and this L gamma D, they are constant appearing here, and this is the subject of a lot of study. If you compare it with the classical Weil formula, if you put a large coupling constant in front of V, then for very general potentials, you can have this asymptotic formula, and the constant appearing here are very special. They are sort of, we call them L gamma D classical, and then you simply obtain this constant directly if you integrate this, you take integration with respect to psi here. So if V is non-negative, whatever it is anyway, so we can pull it out, and then it would be very simple integral, and that's sort of related to some beta functions. Now, from the asymptotic formula, it's always clear that the constant appearing in this inequality are less or greater equal than the classical ones, of course, because this inequality is uniform with respect to V. Now, these inequalities have many applications, and then and in particular, when gamma is equal to 1, such inequalities are important for the questions of stability of matter. And then there is kind of confusion here, because we have one particle Schrödinger operator, and then what is to do with the problem of stability of matter. The fact is that this is just a reduction. If you consider quantum mechanical Schrödinger operator, many particles with Coulomb interactions, there is a way of reducing the problem of stability of these atoms to 1D operator of this type with a fairly general potential V, and then this constant here in this inequality, when gamma is equal to 1, I mean you just sum up the energies due to the Pauli exclusion principle. These constants are responsible for the stability of atoms, and the mathematical problem here is to find these constants so that one can mathematically justify how heavy atoms could be in order not to radiate, basically. So that is sort of, then when you have many electrons, of course, if atoms are heavy, then they start radiating, and then there is no stability. So, and in principle, that's a challenging problem. Now, the other importance, the other application for these inequalities is the theory of turbulence, for theory of Navier-Stokes equation, and the constants are responsible for the dimension of attractors in this theory. And then recently, it's been also pointed out that these kind of inequalities for more or less arbitrary gammas are responsible for the study of the absolute continuous spectrum of Schrödinger operators. So what happens here is that if you plug in a potential, then this potential, depending on how it sort of goes to 0 at infinity, it might pull out more and more discrete spectrum, and then it basically destroys the absolutely continuity property of the continuous spectrum. And then there is a result of Deift and Killip, and later Molchanov, Wandberg, and Nowitzki, who sort of related the problem of the how many eigenvalues you can have, and in terms of these inequalities, and then the preservation of the absolute continuity of the spectrum. So that's sort of basically three applications of this type of inequalities. Now there were a lot of studies, and here one of the questions was to understand when such constants are finite, and then it's completely done. So this is a list of when these constants are finite, and when dimension is 1, the gamma has to be greater or equal than 1/2. I'm sorry about it, it's a misprint. Then dimension 2, gamma greater than 0, and then dimension greater or equal than 3, gamma has to be greater or equal than 0, and gamma 0 means that we study the number of negative eigenvalues. It's a less satisfactory situation with the sharpness of the constants, and there are only following cases when the sharp constants were found. So when in dimension 1 for the square, sum of the square roots of the negative modular of eigenvalues, we have the constant 1/2, and this is twice the classical one. The classical one is 1/4. And this is sharp because you can check it on the delta potential and just the delta interaction. So when gamma is equal to 0 in dimension 1, it's allowed to have this v to the power 1, and then in this inequality, and therefore you can check it on delta function, which produces only one eigenvalue. That's operator of rank 1. And for the gamma greater or equal than 3 in all dimensions, has been proved that there is such a identity that for all such gammas in all dimensions, that the constant here coincides with the classical one. So here it's a list of people involved, and it was shown that by Didier Robert and Bernard Alfer that if gamma is less than 1, that we have this inequality, and they are believers that the conjecture of Liptiering, when the most important one, then L3 in 3 dimension and gamma is equal to 1, then where you really study the stability of matter property coincide with the classical one. They really believe that it's not true, but anyway, nobody can reach this. Nobody proved this conjecture or disproved it. So it's still open, and this is a very important conjecture in this area. Now, we start approaching sort of graph theory. Now, so of course the simplest graph is just the whole line, and for the whole line we have these inequalities and Liptiering inequalities, and what is known that say for square root we have this inequality, and that's exactly what it was described in the previous slide. So 1/2, it's twice the classical constant here. Now for gamma 3/2, and then dimension 1, we have 3/16. It's also classical inequalities, it's classical constant, and that's what appears in the wild type asymptotic 3/16. And then what happens here is that you have this important trace formula saying sort of corresponding the properties of the potential, namely the L2 square of the L2 norm of the potential, and the scattering coefficient A, and then the discrete spectrum. And this is a very important identity, and that's exactly where Deift and Killip made their conclusion that property of absolutely continuity spectrum could be still preserved, and this limiting case when the integral v square is finite. Now, and then also Molchanov, Nowitzki, and Weidberg, they considered the higher formula of this type in order to prove some other in order to give some other properties when the absolutely continuous spectrum is preserved. But if you see that there is a relation, of course, if there is a intimate relationship between these two integrals, so this is constant, and of course if you have more values here, then you have less value here, and then the other way around. So it's sort of it's a very neat relationship. There is another trace formula, which is so-called first trace formula, and that is this one, and from here you can get this inequality. So it's an estimate of the square roots of the eigenvalues from below. So together with this one, you have a quite neat estimate from above and from below on the square roots of the lambdas. Now, but as I mentioned, so this inequality could be obtained from this one because of this property. So you just get rid of it. Log is positive here, so this integral is positive. If you just cross it out, then you get this inequality. Now, let's consider now half-line with some boundary conditions. So we have a Schrödinger operator on half-line, and for me it's convenient to have these boundary conditions, and we always consider this boundary condition rather than it's in the form of the Kostrikin and Schroeder, and you see a bit later why it is so. Now, so the corresponding quadratic form is this one, and then the theorem which I want to present here, and the basically results which we are talking about, it's my joint result with my PhD student at Imperial, Mohammed Osman, who is probably here. And then it's the following inequality holds true. So for any sigma, if potential V belongs to L2, then we just take potentials positive, so for simplicity, so in order not to write pluses and minuses. Then for the eigenvalues, negative eigenvalues, we have this formula. Now, this formula is kind of striking formula because if one look at this formula, I mean, first of all, if we divide by 2, then we have 3/16 here, right? And here in front of this first lambda, we get 1/2. So, and if, for example, we forget about sigma for a while, if, for example, we consider Neumann boundary condition, then we have this inequality, and this inequality is sharp. Now, so in terms of this inequality, what I'm surprised about when we obtain this inequality is the following: that of course, when you change boundary condition, it's rank 1 perturbation. It's not a great deal, and you don't expect very complicated formula. But somehow you know that basically spectrum changes, and in terms of this inequality, spectrum changes. I mean, the inequality itself changes only in terms of the first eigenvalue. So all the other eigenvalues, they have this inequality with 3/16 basically because of this 2, right? So sigma appears, of course, as it appears, but still somehow if you look at this inequality, then everything is preserved starting from the second eigenvalue in terms of this inequality. And then the only changes which come through, it's just the changes with the first, related to the first eigenvalue. Now, let me prove this inequality. So the proof is fairly simple. So one of the way of proving could be to have kind of a trace formula of type which we discussed before. But somehow these trace formula seem to be not that easy, especially for general graphs. So we use this method, commuting method of Ben-Gurion Loss, who contributed into the matrix potential with Liptirian inequalities with the matrix valued potential. Now, so let's consider the first eigenvalue and also the first eigenfunction, which we choose to be positive. And on half line, if we have u1 is an eigenfunction, then we can have we have to have this normalization when x goes to plus infinity, and when x goes to 0, we have this presentation. And we introduce function f, which is logarithmic derivative of the first eigenfunction. Now, the nice property of this f is that if we just take x going to plus infinity, then we have this minus square root lambda 1. It's just derivative of this function. And then if x goes to 0, then we have sigma. And of course, this is natural because of our boundary condition, because boundary condition is precisely that u prime is equal to sigma u1, right? So that is our sigma. And then very easy to check, just taking derivative. You have a second derivative here, and then you take square. Then this function f satisfies this Riccati equation. Okay. Now you introduce an operator of degree 1. This is operator q, and then you immediately check that if you take q star and q, you just open brakes, and you obtain the Schrödinger operator, the previous Schrödinger operator with a shift lambda 1. And of course, you have this natural boundary condition. Now, so the first eigenvalue of this operator, of course, is 0 because of this shift, because the eigenvalue, the first eigenvalue of this operator is minus lambda 1. So when you swap, you preserve, when you consider instead of q star q, you consider q star, then you preserve the all eigenvalues apart from 0, but then you easily prove that 0 cannot be the eigenvalue for this operator. So, but when you do this swapping, then you obtain a new Schrödinger operator, which is very similar in some sense, because it's v missing here. Very similar in some sense to the previous one, but it has a different potential, and this is a difference potential is precisely minus 2 f prime. And what is, of course, clear that the domain of this operator also you obtain by applying this q to u, and then you obtain Dirichlet boundary conditions. So you have a new operator, a new Schrödinger operator with a new potential, which is v minus 2 f prime. But now you have Dirichlet boundary condition. And with Dirichlet boundary condition, it's a lot easier because you can simply extend operator on the whole line and obtain the inequalities which you already know. And that is the following one. So you know that all the eigenvalues starting from 2 to infinity now could be estimated by this new potential, which is v plus 2f prime, with the sharp constant 3 over 16. So all you have to do, you just have to open brakes. Now you just open the square, you get this this term, so v squared. That's exactly what we want. Now here v plus f prime. You remember that we had the Riccati equation, and Riccati equation says that this is true. So if you take v to the left and f squared to the right, then we can see that this identity, so it would be lambda. Instead of this term, we have lambda 1 minus f squared. And now we can simply integrate. So lambda f prime, integration from 0 to infinity, it just gives us this expression. And we have values of f prime at 0, at infinity. We know all these values. It's either minus square root lambda 1 or sigma. And then f square f prime, it's a derivative of f cubed. And that's also, we can integrate and substitute the f cube at the 0 and at infinity, and that would be these two. And this is it. So this is the result, basically. This is the proof of the stated theorem. Now, so you can do similar things with gamma 1/2. in order to obtain inequalities from below. Basically you do the same thing, and you know that from the one-dimensional theory, in particular from the trace formula mentioned before, again, then you have this inequality with 1/4, which is a sharp constant. And then again, it's a lot easier in some sense because you don't have to take square. You just integrate this f prime, and you get this inequality, and that's what you have for the square root. So for the square roots, and again, you sort of lose here 1/2 somewhat. Now, clearly, if you look at this expression and then you look at the quadratic form of this operator, then you immediately see that this property holds true. For example, if sigma is negative, then you have quadratic form would be more positive, and then you would have better inequality, which is absolutely natural, of course. So it's absolutely, it goes in the right direction. So that's sort of, I mean, for me it was surprising that simply this, how simple that this, the boundary condition comes into these formulae in such a simple way. Now, you can do the same thing for the intervals. So it's not much difference because, so what happens on a half line, you have, of course, this situation that you have pure exponential functions, which gives you this, when you take f, which is logarithmic derivative of the first eigenfunction, then you get, at infinity, you derive these exponential functions, and at infinity f is equal to minus square root lambda 1. At the 0 you have the boundary condition, but here if you have two boundary conditions, of course, then you can do the same thing on the finite interval. Here it's supposed to be a. I'm sorry, again, it's many misprints. So you don't gain this lambda at infinity, but you just gain the second boundary conditions, and in such a way. So you get sigma 1 plus sigma 2, and here you sigma 1 cube plus sigma 2 cube, and then that is the inequality for the eigenvalues to the power 3/2. So note that there is no this extra 1/2 or lambda 1 appearing here. It's due to the fact that you integrate over finite interval, and then at the upper point, point A, you have this boundary condition which you take into account, and that comes here. Sigma 2 comes here in front of lambda 1 and here. So you have these couple inequalities. So you have this inequality for the interval. Now, let me discuss a little bit the operator value problems for Schrödinger operators. So what we do now is that we consider Schrödinger operator with potential V, which is a self-adjoint operator valued function in some auxiliary Hilbert space H. And it has been obtained by myself and the team of Alt quite some time ago, that the following trace formula holds true, and then there are two of these. I mean, there are infinite number of them, of course, but these two are important for us at the moment. Later, the similar result was obtained by Weinberg and Molchanov. Now, so again, it's fairly easy to show that this scattering operator, now it would be scattering operator coefficient somewhat. So it's also satisfies this property. It goes very quickly. You obtain it very rapidly by considering Wronskians. I mean, what is interesting here is that A here is an operator in this Hilbert space, and so it's this inequality which we have here. It's operator inequality. There are no traces here. If you look at of course, when you consider the trace formula, what happens here, you have these determinants here and determinants here and then traces here. But what you actually have is an operator valued inequality here. And somehow it's a bit confusing because this operator inequality, the fact that it's operator inequality, we don't need it here. We only need the determinant is positive. This log determinant is positive. That's what we need in order to obtain these inequalities. But the fact that this is a much stronger inequality has never been used, and I wonder how we tried hard to somehow apply the fact that this is operator valued inequality, but so far we didn't succeed, didn't find any interesting examples where it could be applied. But once it's done, then of course from these two formulas we obtain these two formulas immediately, again because this integral is positive and this integral is positive, so we have these two inequalities. So one can think, why do you need this kind of operator values inequality? And then for us, it was important because what we've done is at that time, we considered we using these operator valued inequalities, we were able to obtain sharp Liptirian inequalities for the multidimensional cases, multidimensional Schrödinger operator. And of course, one-dimensional Schrödinger operator is sort of a nice toy model, but the serious problem comes when you consider multidimensional problems with partial differential operators. So, and the idea here was very simple. So just for simplicity, if, I mean, there is an induction process, but if for simplicity we take dimension 2, then what we can do is the following, that we can split our Laplacian into two operators like this, and then consider this as a new operator. And now we take minus out, so this operator has a continuous spectrum negative, and then has positive eigenvalues, because minus is out now. So, and then by variational principle, we simply have, if we take a positive part of this H tilde, then of course we only make the sums bigger. So here I take positive part. So we take the original Riesz means of the negative eigenvalues of the operator H, and then we can estimate it by doing this one. And then we can apply the operator valued inequality which we had before, and then we can write with a sharp constant 3/16, we can have this trace, and this is a positive part, and I mentioned that it's where the discrete spectrum is. And then we apply just again one-dimensional operator. Now we have a one-dimensional operator. It's just with this depending on the parameter x1, for each x1 we can apply Liptirian inequality in one dimension, and that's what we obtain. And then turned out that this constant is sharp. So you can obtain sharp inequalities. Now you can do the same thing, similar things for the operator on the half lines with some Dirichlet boundary conditions where sigma is a self-adjoint operator in auxiliary space X, and of course V is the same. So we consider standard Schatten classes, and the theorem which we have here is the following. So if we have V from L2 for this particular inequality, and if sigma belongs to the Schatten class S1 intersect with S2, then we have this inequality. So it's basically the same inequality as we already had before, but of course again, instead of just values of sigma and V's, we substitute traces here. We substitute traces. It's a fairly standard way of doing it. In fact, Ben-Gurion lost when they prove such inequalities, when they applied such inequalities for operator valued potential, then they done it for matrix cases, and that is sort of following their proof. We can prove this inequality. And of course, this inequality holds under condition that sigma is from trace class and V is from trace class too. So we have this couple of inequalities. Now, so that is on half line, and of course it's not a sort of rocket science to also to have similar inequalities for the interval. for the finite interval, and that allows us to formulate a result on quantum graphs. And this is the following. Suppose we have gamma is a finite graph with finite number of vertices and finite number of edges, and also we have a finite number of leads. We denote n the number of leads. This is semi-axis going to infinity. So let H be a Schrödinger operator on the graph, and we consider each vertex this boundary condition where sigma Hermitian matrix n times nj times nj. So we have for each vertex we have nj number of edges. And then that gives us the following result. So if B belongs to gamma 2, then we have this inequality. So here we have n, which is number of the leads, and it comes like this. And then we have the sum starting from k2 to infinity. Here we have just traces at every vertex, and here too. And then the other inequality is sort of dual inequality. Inequality for the square roots is also very similar. So that is the thing. Now one can sort of start thinking about how one can use this inequality, and we don't have, as I mentioned before, we don't have trace formula for arbitrary graphs, and that would be very interesting to obtain if it's possible. But one can think that it's just that the question of absolutely continuity of the spectrum of graphs. If we think in terms of how the discrete spectrum related to the continuous spectrum, in terms of trace formula at least, then they sort of the discrete spectrum, as I mentioned, the potential and the boundary condition can take from continuous spectrum and make negative eigenvalues. So can they destroy the absolutely continuity property of the spectrum? And it was shown by Dart and Killip that integral v square belonging to integral v square finite, or v belonging to L2, which is a limited case, is still preserve the absolute continuous spectrum. I think this formula also might give a hint also that why and when the absolute continuous spectrum could be preserved for the Schrödinger operator on graphs. And if we have of course, if we have finite number of edges and finite number of leads and so on, so it's basically we talk about finite rank perturbation. Of course, it doesn't sort of really destroy the absolutely continuity property of spectrum. But if we have the infinite number of vertices, for example, then what this formula gives a hint is that at least these kind of traces have to be finite. So I think it's sort of something to think about. Now, just one of the examples is that we can do, of course, it's just this delta coupling, and in particular, so when we have standard delta coupling, which provides a continuity of the at each edge going into the vertex related to the vertex Vj, and then also this property on the derivatives. Then the previous formula is reduced to the following one. So here we have a number of vertices. Here we have alpha. I don't know why. I don't want to. Let me put here. There is no j here, and also something is wrong here. So here it has to be L, and summation with respect to L and alpha does depend on j. Let me just keep it this way. So here we have alpha, number of vertices, and here we have this trace sigma at each vertex. and of course, if alpha is equal to 0, which corresponds to this free or Kirchhoff boundary condition, then this term just disappears, and we have a nice formula related Liptirian inequality for the graphs. Now, so that's sort of basically the graph theory. I have maybe a few minutes.
Oh, I think you have 10 minutes.
Oh, still 10 minutes. Okay. So I also wanted to mention something which is not really related to graph, but also related to the other story. And this is so originally when we started sort of thinking about the boundary condition problem, we were thinking of the situation for the multidimensional Schrödinger operator with some boundary conditions. And in particular, for example, if you consider half space in, say, in 2 dimensions, then we can consider the Schrödinger operator in 2 dimensions of this type. So, and then we introduce a boundary condition similar to what we had before. So then one of the results which we also obtain is the following, that if we consider the sum of a k, some of the eigenvalues of the operator h, of this operator on half space, then we have this inequality. So here we have L2 norm of our potential. Here we have a something which is slightly different, and here we have also the contribution of the boundary condition. So how can one prove it? One can do it as follows. Again, what we can do, we can introduce, we can rewrite our Schrödinger operator, having the same idea. We can rewrite our Schrödinger operator in such a form where here we have an operator h tilde, depending on the variable y, which comes through the potential v. Of course, here we have this is one-dimensional operator depending on the parameter, or with the boundary condition depending also on the parameter y. Now, for the sum of the eigenvalues, there was a result recently published in GEMS by Jean Dalbot, myself, and Michael Loss. We have this inequality. Now, this inequality is not sharp. We don't know whether it's sharp or not anyway, so the constant appearing here, not clear whether it's sharp or not, but it's still sort of best standing constant at the moment for the sum of the eigenvalues of multidimensional Schrödinger operator. So in 2 dimensions, in particular also in 2 dimensions, this is the constant, and that is what we have. So we can have a trace of a tilde. So it's again operator valued approach for one-dimensional Schrödinger operator, and then we have this trace trace of the positive part of this operator h tilde depending on the parameter y, and then it comes to the power 3/2. And once it comes to the power 3/2 for each y, again we have operator on half line with some boundary conditions, and we apply a result which we obtained before, and that is a sharp result for at least for this trace, and we can write it as follows, where mu1 is a eigenvalue depending on y of the operator h tilde depending on y. So the mu1 could be, there is a simple way of estimating square root of mu1, and this is through the integral for more or less arbitrary boundary conditions. Of course, self-adjoint, we consider only self-adjoint cases here. So through the integral of v, and this is inequality. I mean, one can do it through, for example, applying Biermann-Schwinger principle. So, so just substituting this inequality into this inequality, we immediately obtain the result. So this is a final theorem, which again, it's interesting how the the boundary conditions comes in. It's sort of also, it's integral sigma to the power 3 over the minus infinity with respect to y. So again, so there is again question of what kind of, I mean, if you want to consider the property of the absolute continuity of the spectrum of this Schrödinger operator, for example, then again, with some boundary conditions, say on half line, then again, one can get a hint here that, of course, sigma or the boundary condition has to be somehow involved, and that's what the involvement of sigma shows here, and that's possibly could be almost necessary and sufficient condition for the preserving the absolute continuity of the spectrum. Now, say in 2 dimensions, but multidimensional cases are extremely complicated. Nobody really knows how to prove the necessary and sufficient condition. In the 1 dimension, things are sorted out, but in multidimensional case, it's a lot more complicated. The other thing, speaking about this kind of approach, there aren't any inequalities, spectral inequalities for, say, Schrödinger operator with fairly arbitrary boundary conditions, depending on the boundary condition, even for bounded domain. So as we could see that we applied here operator value to inequality. We considered here the inequality on the half line with some boundary condition, but also we could consider the inequality, corresponding inequalities on the interval, of course, and that sort of also gives a hint that maybe we can consider, say, at least here one can easily obtain some results on the strip, for example, or in a more complicated domain, or even bounded domain. So what would be the inequalities for the eigenvalues, or say for in 2 dimensions, it's for the sum of the eigenvalues for Schrödinger operator with some more or less arbitrary boundary conditions, and how they depend on boundary conditions. This is something to do for the future, and we sort of haven't done it yet, but we're hoping that we shall continue this study. So thank you.